and I enjoy going out and giving information to other people. Science can be communicated without being dull. It can be communicated in interesting ways.
Harnessing radiant energy.
So nanoshells are nanoparticles, so they're materials that are billionths of a meter in diameter, and they consist of a very small speck of glass coated with a very thin shell of gold. And based on how we design these particles, the size of the glass and the thickness of the gold, we can make them absorb light at different wavelengths and convert this light into heat.
Is there a theme that can be observed?
Chemical analysis of chloroplasts shows that chlorophyll and other compounds are organized on the thylakoid membranes in a systematic way. When light strikes the thylakoid membranes, chlorophyll and other associated pigments are oxidized, which causes the release of electrons. The electron flow initiated by this input of light energy is coupled with the formation of the compound adenosine triphosphate, or ATP. This reaction is known as the light reaction of photosynthesis.
Magnetic bacteria. The invention of the compass began a whole new era for humankind. By tracking the Earth's magnetic field, sailors could always find north and so could travel around the globe. But the compass was nothing new to a kind of ocean bacteria, says Richard Frankel.
These are bacteria that may have beaten us by about 2 billion years. And the way they do it is they actually manufacture for themselves within their body a kind of magnetic compass needle.
Frankel is a physicist at California Polytechnic Institute. He studies these special kinds of bacteria, known as magnetotactic bacteria.
They've been able to learn how to mineralize, to make minerals inside of themselves, much the same way we make minerals that make bones and teeth. They actually take in iron that they find in their environment and they manufacture the particles of magnetite within themselves and line them up in a chain. In fact, the bacterium has a backbone.
That backbone helps orient the bacteria in the water. Not just backwards and forwards, but up and down as well, since the Earth's magnetic field is not actually straight, but at an angle to the ground. But the magnets don't just help the bacteria get around. They provide useful information for humans as well. When these little bacteria backbones got fossilized over the ages, they left a permanent record of how the Earth's magnetic field lay at the time.
Particles like those made by the bacteria are permanent magnetic recorders, you might say, of the Earth's magnetic field.
Individual atoms all have a magnetic field around, in, say, a big block of copper. The atoms all face in different directions, and so the magnetism cancels out. But in a magnet, all the atoms line up like soldiers in a row.
Sort of a fascism, an electronic fascism, where all of the atoms line up in parallel. And so the combination of the billions and billions and billions of atoms operating in concert is what gives you the strength of the few materials that are really magnetic, like iron, cobalt, nickel.
The tiny magnetic fields around the individual atoms add up to make a powerful magnet.
We can look at these very tiny crystals of magnetite associated and embedded in the Allen Hills carbonate globules. And we can either look at them in the carbonates or we can extract them out of the carbonates and use a transmission electron microscope to look at these crystals. So these crystals are no longer that small. We can get a real good idea of what the chemistry of these crystals is like, what the geometry, what the shape of these crystals is like. We can get a good idea of what the size distribution of these crystals is like. And when we compare all of these different chemical and physical attributes of about 25% of these crystals from the Allen Hills carbonate globules, about a quarter of them, they are indistinguishable from these little magnetite crystals that are formed by magnetotactic bacteria here on Earth.
So, Dr. Beater, which way would a compass needle point in space?
Magnetic fields drop off very rapidly as you move away from the source.
Oh, I see. So in order to see the north and south pole of a planet, you have to be very close or on the planet.
You have to be fairly close. I'll give you an example. The Earth is about 6,000 kilometers in radius, and if you're 30,000 kilometers away, the Earth's magnetic field would have decreased to about 1% of what it is on the surface. Again, if you're within about 5 diameters of a star, you'll see a very similar size of magnetic field to what you would on Earth. And again, the field pattern is a rather complicated one, so which direction your compass points depends on where you are with respect to the rotation of the typical star. But it's a reasonable field out to, let's say, several million kilometers away from the star. Mind you, that's very close, and it'd be awfully hot at that distance.
Captain's log, no star date. For us, time does not exist. McCoy, back somewhere in the past, has effected a change in the course of time. All Earth history has been changed. There is no Starship Enterprise. We have only one chance. We have asked the Guardian to show us Earth's history again.